Okay, so I hope it picks up the audio from the microphone. Anyway, so we're here to discuss the test first. Actually, let's do a couple of quick announcements here first. So I'm going to the schedule here. Today we're in week 10. I moved stuff down a little bit. So I updated last week's notes, and very briefly these updates. So I went to this Android birthday party on Monday. So this was part of the Mobile Mondays series at Morningstar, and I thought this was actually time very well spent. So you might want to keep an eye on this meetup. This is the first event I actually attended, and they had these pretty much lightning talk presentations. So they had this person who gave a brief overview of their WaitBot app, and we might have him as a guest lecturer if we can, just give a brief presentation if we can agree on a mutually convenient time. Then we had him, and he gave some really great insights on some great tips on actual technical aspects of Android development. So you will see some of those actually make their way into the class, and then there were a few other interesting presentations, but they were all pretty much in the lightning talk format, meaning 5 to 10 minutes per presentation. So they kept it really breezy, and time went by pretty fast. And this one is also interesting. So Martin O'Shield, he has this group called Software Defined Radio, and so he went over a little bit, but he also has a really cool story to tell. So he was actually he was setting up an ad hoc mobile phone network using these TV tuner cards that you can use for watching TV on a computer. So by hacking those, you can actually transmit and receive at any signal frequency, pretty much. And so there's basically a project out there where you can do pretty much any kind of radio transmission and reception with that. So he used it to set up it's almost like having your own mini cellular tower, and so he's able to make phone calls using that, by hooking up to his own little network. And then the other thing he demoed was an Android app where let me remember. I think he hooked up this kind of TV tuner card or USB stick to an Android tablet, and then the app was basically showing the frequency band, and you could tune into local radio stations using that. So in other words, the part that defines the radio functionality, all the processing, all the functionality that a radio has to have, other than just the circuit that is connected directly to the antenna and does the oscillation for transmitting or receiving radio waves. Everything else for processing them, for converting those waves into sound, which is what a regular audio radio does, all of that stuff is done in software, and there's this basically Android port of that project. So this was a nice way to end that set of presentations. Let's see, one other noteworthy one was this Pebble watch. It's not on here, but so Pebble is like an accessory to Android devices that communicates with them through Bluetooth, and it's basically so that when a call comes in or a text message, you could just look at the watch instead of taking out the phone, and a few other things like that. So increasing numbers of those kinds of products coming out, including Google Glass is that type of product as well, like an accessory that connects to probably an Android phone or tablet. So anyway, just wanted to get this on your radar so you can consider checking out this one and possibly others. So Meetup has this funny thing, so I could press one of these buttons and then they would get notified and then they can say good to see you too, stuff like that. So that's the social touchy-feely part. But anyway, it's a good thing that we have these interesting events out there. And I know it conflicted with class for some of you, so that's just the way things are, with classes being basically after regular work hours for the most part. Okay, test 2 results, we'll get to this in a second, and I posted a makeup opportunity, so that you've probably seen a lot of traffic on Piazza. So there's a test makeup opportunity for those of you who lost points on problems 3A through H. So it's basically redoing that as working code. You can look at the details on Piazza. So I just wanted to give everybody that opportunity because I think it's an additional learning channel. So the experience is different between taking a written test within a very short time and doing the same kind of stuff as a project and having basically control over your time. So I want everybody to have the opportunity to have these complementary experiences. Okay, so please look at that announcement and let me know if you have any questions. But it's basically taking what's on the test paper and redoing it as actually working Java code with a Gradle build file. So you can start with one of the existing examples and then populate it with this code, etc. So you can have you can start a discussion if there are any questions about it. Just tie a discussion to that post. That would be the easiest way. Okay, now the test results. So class average is 10. So anything 11 and up is good. Okay. And anyone whom I'm worried about would have heard from me by now. So if you haven't heard from me, I'm not worried about your performance. So just a couple of other announcements before we actually discuss the solutions to the test. So if you're interested in exploring advanced programming languages topics, so I'm scheduled to teach this programming languages course this coming spring. And I just updated the textbook. So I'm basically decided I was going to do this in Haskell, but I decided to do it mostly in Scala for a number of reasons. Okay, so what you would get out of this course, if you are considering this, so you would have some experience in Scala, and that's an increasingly good language to know. On Monday, I just got a call from a Loyola alumnus who is looking for people who know Scala and Clojure also. So, and then also Python, and now he said increasingly the Go language. So he's focusing on companies that develop free and open source software as part of their business model, and these are the languages he mentioned. So he was particularly looking for Scala and Clojure. So anyway, the way it's going to be structured, there's going to be basically looking at some advanced object-oriented and functional techniques, some concurrency topics as well. And then there's going to be a component where, based on this book, which gives kind of an overview of a number of languages and various other resources, there's going to be an opportunity to look at a wide range of languages. So everybody gets to basically present about one, but also obviously see the other students' presentations about all the other languages. So you get that part, basically a lightning talk pretty much at the end of every lecture, or every other lecture, 2 lightning talks, something, depending on how many people actually sign up. But yeah, that's going to be in the same slot as this class in the spring. So yeah, these are some sample topics, although it's going to change a little bit from this, but the basic set of high-level topics is going to stay pretty much the same. There's going to be a little more functional programming than what's in here. Anyway, so that's one. The other one is this series of seminars that are scheduled on Friday morning. So there's one that Dr. Mark Albert runs, there's one that Dr. Honig runs, and then there's one that Dr. T and I run together. So these are basically opportunities to get involved in research. So let's see. Let me actually update this with the proper links. That way it's more convenient. So I'm just going to put a link here to the PL course. So that's there, and then I'm going to put a link to Pervasive Seminar. So this is just the one that Dr. Theo Rothukal and I run. But the other ones are going to be similar in terms of the research focus. Okay, oops. So that has some, so ahead of time what you're getting into. All right. Any questions? Any organization? Yes?
You used to cover the F# in the 471.
Right. So I'm going to focus mostly on Scala. And let's see. I'm going to provide you with another link that can give you an overview of Scala versus Haskell versus F#. So I'm going to put this in here as a resource. This is on my GitHub site. So here. So yeah, this will kind of give you a little more of an idea of some of the topics, and there's kind of this assessment of the main contenders. So Haskell, Scala, and F#, what their strengths and weaknesses are. Or let's say what their relative strengths are. That's how I should express it. All right, looks like we should be able to return most of the tests. That's good. There you go. There you go. All righty. Just the time, okay. So let's transition to that. Any other organizational questions or questions about these upcoming courses? Okay. So let me switch over to the test solutions. And yeah, try to take notes. You know, I don't like to send these around. So take notes and ask questions. Anyway, so 1A, all right, so this is why I emphasized, and not that many people nailed this one. That's why I emphasized that super is always statically bound, right? So when you look in class, in the definition of method f in class D, D's f returns 7, E's f returns 11. And we're invoking G, so G returns an unqualified f, meaning this dot f, right? So just f is a shorthand for this dot f, and that's dynamically bound. And then plus 5 times super f, and that's statically bound, meaning look for f starting in the static superclass of the class where this method is defined. So meaning we're looking for the class where G is defined, that's D, and the superclass of that is C. So in other words, super, and then the question is, does C have a method f? And it does. So therefore, super.f in D always means C's f. And now you can calculate the answer. So invoking G on an instance of D, where f returns 11, would be 5 times 3 plus 7. Sorry, I got it wrong. So in D, it returns 7. Let me say it. So we're invoking G on the instance of D, where f returns 7. So the first part of the sum, the first term would be 7. The second part is always the same 5 times super f, which is always 5 times 3, or 15. So D's G, invoking G on the instance of D will be 7 plus 15, meaning 22. And in the case of G invoked on the instance of E, the first term will be the f from E, which returns 11 plus 15 is 26. Any questions about this? I'll pull that up here, just. Right, so that's that part. All right, now, next problem. So what are the static and dynamic types of X and Y, respectively? So how do you answer this? Well, first thing is you look for the definition of X. Okay, that's defined here. And what about Y? Okay, that one's defined here. So this tells you what the static types are, because that's what static types are. The types used in the definition or declaration of those variables. So I in both cases. Okay. And then what about the dynamic type? Well, there you have to look exactly what happens with those variables dynamically. So X gets initialized to an instance of D, and Y gets initialized to an instance of E. So at that point, their dynamic types are, or X has dynamic type D, and Y has dynamic type E. And then the dynamic types don't change in this program, but there's nothing in principle that would keep us from later assigning an instance of D to Y, and at that point, if that were the case, the dynamic type of Y would change from E to D. So that's the nature of the dynamic type. It's not necessarily the same throughout. It depends on things that you don't know until the program actually runs. Because there could be a piece of code saying, if user input equals something, then assign an instance of D to X, else assign an instance of E to X. So that is something the compiler cannot determine because the compiler cannot predict what the user will input. Okay? So that's why this is the dynamic type. It can change throughout the execution of the program. But in this particular case, we just set it once for both X and Y. So that's why there is a single answer. The dynamic type throughout the life of X and Y is D and E, respectively. Any questions? Okay. Now, what's the problem with the F in F? The method F in class F. So remember, just invoking F means this dot F. And then if you're doing that on the instance of F that you just created, so syntactically this is fine. You know, it's just we're not defining a variable to refer to this. We're just saying, okay, here's my expression new F. That means that expression evaluates to an instance of F, and then we can talk to that instance. And we invoke the method F. So this would be this instance of F. And when we invoke the method F, it goes in here and it says, return this dot F, meaning invoke F again on this, which is this instance of F. So we get in here again and again and again. So it's infinite recursion on that method F in class F. All right, any questions about that behavior? So the way to fix it is, for example, by using super, if that's what we wanted. Or just maybe, you know, depending on what you're trying to achieve, invoke some other method or so. But you know, assuming that we're trying to get some kind of inherited behavior of F, we could say super dot F, and that would break the recursion because now we would pick up the F in the static superclass of class F, which would be E, and would return 11. Any questions? Okay, very good. Now, so why must the class C be declared as abstract? So what we see here is C says, I implement I. And I says, oh, you have methods F and G. Oh, no, I have only method F. Can I still implement you? And then the compiler says, well, we'll let C say it implements I, but it has to say also that it's not a full implementation of I. And that's what the abstract means. That it's a partial implementation of I, or it just says, well, even though it might be a full implementation, let's say if C implemented F and G, it could still say, well, but I still want to be an abstract class, meaning no one can create direct instances of C. So that's a possibility. But if the class is a partial implementation, it has to say it's abstract. If it's a complete implementation, it can say it's abstract if it wants to. Okay. All right, any questions about problem 1 before we move on to, so that means the answer is the second one here. So it has to be declared as abstract because it's only a partial implementation of I, in the sense that it doesn't implement all the methods that I specifies or requires. Okay. All right, now problem 3. So yes, sorry about having skipped problem 2, but there was nowhere to fit a problem 2, so that's why we didn't have a problem 2. It just wouldn't fit on the 4 pages, and I don't like the test to go over 4 pages. All right, that's already challenging enough. Anyway, so problem 3. So now you might want to take notes, careful notes, in case you want to do the the re-implementation in code. So I'll try to keep it brief, but ask questions if you have specific questions, if anything specific comes up. So this is very similar to the shapes project, meaning project 3. The crucial difference, and this is going to be discussed in those questions on the last page. The crucial difference between this example and project 3 is this is without visitors, and project 3 is with visitors. Other than that, it's the same idea, composite pattern, meaning, as you answer later, decorator and composite. So this kind of hierarchy. So here we can have arbitrarily complex trees of fruits. Okay, and very similarly, we have to have some starting points for building a complex structure. Meaning, in recursive thinking, or correspondingly in inductive thinking, you have to have a base case that you can just say, okay, here's a particularly simple instance of this kind of structure. So, for example, just a peach. We're saying, just a peach fruit by itself, that is equivalent to a tree, or that counts as a tree. All right, and now we have to implement the behaviors. So that has size 1, just like circle. And to harvest a single fruit, we just add the single fruit to the bag. So this is kind of the base case, like circle and rectangle. And now branch, which class from project 3 does branch correspond to? Group, exactly. So branch is like the group of shapes. So this allows us to bring in nonlinear structure, okay? And to compute the size of a branch, and this is kind of the point I want to make here. That's why we're recapping this test. So if you have a branch node here, and then you have subtrees, the children, how do you compute the size of the branch? How do you do that? So this is what we're having here in the test and in our project and generally in this class is we're using an approach where we're structuring our code in object-oriented ways, using classes, methods, and object-oriented design patterns, but the underlying algorithms can be presented in different kinds of ways. So the underlying algorithm here is just basically a tree traversal, where we say, well, when you look at a single peach, so let's draw it like this, whatever. So I'll annotate this, a peach. Okay. So when you're then defining methods or functions on these kinds of tree structures, you usually have a case distinction, right? You say, well, if it's the base case, then we return the answer directly. If it's not the base case, we have to compute the answer recursively. That's what we're seeing here. Where is that case distinction? If it's a peach, do this. If it's a mango, do that. if it's a branch, do something else. Where is the code for that branching? Is it somewhere in the test? The code where you're actually making that branching happen? Or is it in code that you write? Do you have to write that code, or do you even have an opportunity to write that code? No. So where is it? Where does that take place?
Tree interface, the implementation of tree kind of makes it automatic.
Yes, yeah. You were on the right track there. That's right. So I mean, what we have. So these are two specific instances here, right? So if we look at our class hierarchy, so we have tree, fruit, and branch, okay, and other stuff later. So that's true. The interface kind of ties them together. So on anything that has the tree interface, on anything whose static type is that tree interface, we can do what? We can invoke methods defined in that tree interface, right? And what happens then? What occurs then? So if that object on which we're invoking one of those methods, if it's a peach, it does one thing. If it's a branch, it does something else. So that's where that decision is made somewhere. It's made behind the scenes, basically, right? Because it happens automatically. That is handled, that branching is dynamic method dispatch, right? So in other words, so you have a size method in fruit, you have a size method in branch, and dynamic method dispatch is this case distinction. That's where the code is. It's inside the language implementation, the runtime system. Does that make sense? You don't write it. You just say, well, for branch, the behavior is the code right here. For fruit, the behavior is the code right there. But the case distinction, if my argument is a fruit, choose this code, or else if it's a branch, then choose that code, or if it's something else, then do something yet different. That is implemented as the way dynamic method dispatch works. Does that make sense? So in other words, when you have an invocation of a method such as x.size, the argument is given this kind of special position of the receiver. And here we say, well, let's do a case distinction based on the type of the receiver now, on which the static or the dynamic type. Exactly. That's what it's all about.
What did you say?
The dynamic type. Because the static one, I mean, it could be tree in either case, right? So that's not even a class. That's not even a class. That's just an interface, a specification. So in many cases, the static type isn't even a concrete class. So in other words, we really want to know what is X really? Is it this or that, or a cluster or whatever? And perform this invocation. Look for the right method based on the dynamic type of the receiver object. And again, so this is like a function argument, but because it's used to make this decision, it's given this special position as the receiver preceding the method name, right? So in non-object oriented languages, you would write size x, right? And then you would say if x is a peach, then return 1. Else, if it's a branch, then do the recursive computation. So that recursive computation algorithm is the same. We're just structuring our code in such a way that this explicit branching that we would have in non-object-oriented solutions, that becomes implicit in the form of the general dynamic dispatch mechanism. Okay, that's right. So that's what this is basically about. And then visitor is a way to, in a way, bring back the branching. In a way. Not, there's still no explicit if else, but it's kind of done in such a way that when you look at size as a visitor, like in project 3, you will kind of see the branching in the form of the visit, this kind of thing method, visit that kind of thing, right? So it's kind of like that, yes?
Going back to the x dot size, what if you defined, or could you define x as a tree x equals a new mango? Okay, but then in that case, which method would it call?
Okay, so let's look at this example. So you say tree x is new mango, and yeah. So let's take a look. So what's the So we'll look at x. Static type, obviously tree, right? Dynamic type, well, assuming that we're invoking it right away. So nothing else was assigned to x. So dynamic type is mango. So dynamic dispatch says, start looking for the size method in mango. So we look here. Oh, it doesn't have its own size method. Then no problem. Then let's look in the superclass. And there we find the size method. So we invoke that one. Does that make sense? So that's how it works. But the branching is kind of the part where we say, well, what is the dynamic type of the object? And again, I'm using the term type to mean things like interfaces, classes, and so on. Things you can use to specify the characteristics of an identifier. So type used broadly in that sense. So in Java, those things are called reference types, right? Arrays, interfaces, and classes. Okay, very good questions. Any other questions? So what I'm going to focus on now is just the recursive algorithm. So that is kind of language independent. If you're just looking abstractly at this data structure, so you have a structure that has this tree shape and has children. And if you try to drill into the children, then you're making the algorithm really unnecessarily complicated. What you want to do is you want to look at these children abstractly and just invoke methods in their interfaces. And in this case, they all have the same interface as you, meaning tree. So what you do is, what's this guy's size? So he comes back with an answer. Or what's this one's size? Comes back with an answer. So all of these have, let's say, different answers hypothetically, right? And then that means this has 3 fruits somewhere in the tree. This one has 7 fruits somewhere in the tree. So then the answer for the whole tree rooted here, for the tree that we're looking at here is, well, you just have to add up these partial answers. So most of these kinds of tree-based algorithms function like this. Get partial results, one for each child, and then combine those partial results in some meaningful way. So in the programming languages class, we're going to look at these kinds of algorithms in a more advanced way, where we can kind of talk uniformly about algorithms on lists, on trees, and on other kinds of structures using certain algebraic methods, and then it all becomes the same, which is kind of cool. Okay, so why is that useful? Brief preview. because then you can reason about it more uniformly. You know, whatever theorems you can prove, they apply to basically a wide range of structures in this way, and you don't have to prove them again. And those things that you can then use for optimizing your programs or transforming them in certain other ways that they become simpler or perform faster. Okay. So that's basically the algorithmic part here. And so in general, obtain a partial result by applying the method recursively to each child and then combining. So that's why we get basically this kind of code here. Say, well, for each child, okay, that's how you want to read this. You know, so for each child T of the current branch node, add their size into the sum that you're accumulating, and then you're returning that sum. You know, it's an imperative way of computing it, you know, one after the other. Now, to emphasize this point even more, so it's the same idea for harvest. So in other words, the algorithm for size and harvest is basically the same, meaning that for size, you invoke a method that gives you a result for each child, on each child. And with harvest, you also invoke a method on each child, but that method happens not to give you a result that it returns, you know, but it has an effect on other objects, such as the bag, you know, so it stuffs more fruit into the bag. Okay, but the key thing is, so here we're defining the size method and we're recursively applying the size method. And here we're defining the harvest method for the composite node or the tree node, branch node. And here we're invoking that method recursively. You know, so this recursion is what's in common, this recursive pattern. For each child, invoke the method we're defining recursively on the child. That is in common between this and that. Does that make sense? And that's also, you know, with or without visitors, it's still the same. Except when you write this as a visitor, instead of invoking a method, it's passing a visitor object to the accept method. That's really the only difference in that sense, you know, going between non-visitor and visitor. So here, non-visitor, so we have an explicit method invocation. Visitor, same algorithm, exactly the same algorithm, but passing the visitor recursively to the accept method on each child. Any questions? So this gives us pretty much a complete picture, you know, for the base case and the composite node, like a branch or a group of shapes. So now to make things more interesting, we're introducing this this decorator, which, you know, the cluster is a decorator, branch is a composite. So which class in project 3 is cluster similar to? Yes, exactly. Very similar to location. So it just it's a decorator. It maintains the same original interface, right? But somehow wraps a little bit of extra information with slightly modified behavior around the original object. So we can make this tree look 5 times as big by having a little cluster with factor 5 around it. That's the idea. You know, just like location, every circle is, you know, every circle is kind of location independent, or is maybe by itself interpreted as being centered at the origin. And then with a location node, we can say, oh, it's really meant to be over there. Similarly here, well, here we have a tree, but with a cluster node, it's meant to behave as if it had many more fruit, given that multiplier factor. Okay, that's the idea, and we'll have to implement the methods accordingly. Now, so let's look first at size and harvest. So for size, again, now the cluster has just one child, just like location. So the size is, well, if the child has a certain size S, and the cluster is supposed to make that child look like it has get multiplier times as many, that's the size you want to project outward, right? So the multiplier times the real size of the child. And for the harvesting, you can kind of repeat the harvesting as many times as your multiplier. But again, in the harvest method, so this is something I want to emphasize very clearly. When you make the recursive call, so the only things that you can add directly to the bag are what? Fruit. Not clusters, not branches. They have to be fruit. Therefore, you cannot use the add method on a child, because the child might not be a fruit. These are arbitrarily complex trees. So that's why always recursively just use the method that you're defining. Same here, size. Just let the recursive invocation come up with the answer. If that thing happens to be one of the base things, it will automatically invoke the base case, like this one, okay? But don't try to do it when you're doing the recursive definition. Don't try to invoke or provide base case behavior when you're actually in the process of giving a recursive definition. Okay, so now the harvest method, again, we just saw this, so just repeat it as many times as the multiplier, and you have that many more fruit in the bag as a result. Meaning here, let's say if this is 5 times this tree, so here you have 26 fruit in this tree, and you do this 5 times, you have 5 times 26 fruit in the bag. And that's as if the tree had been that big. And that's the purpose of cluster. So we're basically doing the right thing here. Now, how to grow a cluster? Well, we can say, okay, and let's look at the actual result type here. So grow should return another tree. Always pay attention to the return argument. So size has to return an int. Harvest should return nothing. It should just have an effect. And grow has to return a tree. So the cluster, to grow a cluster by a certain factor, there are 2 ways to do that. Just like there are 2 ways to change the location of a shape. One would be to replace the single location wrapper with one with updated values, or just to wrap another layer around it. And you could do the same here. So here we're saying, okay, let's just replace the wrapper, or we could simply have said this. Right? And in the second case, it's very simple, and it just introduces another layer. So if we do a lot of growing, we get more and more layers. So that might or might not be a problem. All right. And then the funny thing is, if you do it like this, it becomes the same as there. So, in other words, growth is always the same behavior, potentially. Just wrap a cluster around it. And that's actually nice little simplicity, a uniformity here. So, how could you factor out this common behavior? What would you need to introduce to our class hierarchy here? Again, the objective would be, so this is outside of the test. So here's our class hierarchy. This is an interface. And we just observed, okay, grow for fruit and grow for branch and grow for cluster can be all the same. And what do you call when you have repeated code like that? Well, you just call this repeated code, your code duplication, right? Code duplication. Is that a good thing or a bad thing? That's a bad thing, exactly. That's right, exactly. So it's an example of what in the refactoring community is called a code smell. When there's something that's just not right about the code and that you'd rather get rid of, right? The refactoring community talks about that. So they have a list of smells, and so they probably talk about this in the episode, right? I haven't listened to it for a long time. So you have a list of possible smells, such as code duplication, and then you have a set of refactorings, like a refactoring catalog. And now we're looking for the refactoring for getting rid of this smell. So we have this situation. How do we do it?
We can implement this code in the superclass.
We can implement a superclass for what?
We can implement this function in the
Oh, this function, yeah, exactly. So here,
Yeah.
we're on the right track, except this is an
Interface,
right.
but we need an abstract class.
exactly. So we introduce an abstract class, and then we can pull the common repeated method up. So it's called, pull method up. So we have to have this, and we have to have an abstract tree here. And then the grow method could live here. Very nice, that's right. Does that make sense? So this gets rid of the smell. And what do we observe about this refactoring in terms of the functional requirements or the actual functionality of the code? Does this refactoring change the behavior of the code, or does it leave it unchanged? Unchanged, exactly. In fact, the refactoring community defines a refactoring as a modification that leaves the behavior of the code unchanged. That's really the whole point. It's making the code nicer and cleaner, but without making a change to the behavior or to the functionality. So the idea is, let's say, so it ties to automated testing by saying, well, I make the refactoring, and a lot of development environments support these kinds of refactorings. There's even a menu item in IntelliJ or Android Studio. Eclipse also supports some refactorings. So renaming is a very simple refactoring, like renaming a class across your entire code base. It's non-trivial because all the uses of the class have to be hunted down, and that's why it's good if the IDE does this kind of stuff for you. So this one is structurally less trivial, where you're actually introducing a new class and all that. So the IDE can do some of that also. Okay, excellent. So the idea with the automated testing is you perform the test, then you do the refactoring, and it shouldn't change your test results. Right? So if you have a comprehensive test suite, that's what you expect to observe. And if anything changes in the test results, it means it wasn't a clean refactoring what you did. Okay, great. So that was kind of the mini digression on refactoring, incorporated in our test discussion. All right, any questions so far?
Just one question.
Sure.
Regarding IDE, you mentioned that Eclipse has ability to do some refactoring.
Little bit, yeah.
So is it just only one IDE that is limited to refactoring, or can do too much on the code? And if we have an IDE which is Eclipse, can we use it to do refactoring?
Yeah, so I mean the
Or as a limitation of those IDE?
yeah, so right. So these are IDE specific capabilities. So in other words, to what extent does a specific IDE such as Eclipse or Android Studio, IntelliJ IDEA, same thing, support certain refactorings, and renaming is supported, for example, by basically all IDEs. The renaming of, let's say, a class or a method throughout your entire code base, right? Not just, obviously you can use just an editor to rename a method name in the definition of the method. The point is, if you rename the method in the interface where it's defined, you want to make sure that everywhere that method is called, it's also renamed, so that afterwards everything works just like before. Then it's a refactor. Otherwise, it's just a kind of a partial renaming that then causes a compilation error. Right? So that's the kind of stuff I'm talking about. So again, every IDE decides which refactorings it wants to or can support. Does that answer your question? Okay. Okay, cool. So now we're going to apply these classes. So here's a definition, and the difference is it's similar to the shape project in the sense that we can just kind of write a nested object tree like this with the indentation suggesting a particular tree structure, right, or reflecting the tree structure. And yeah, that should come back with size 5. We see 5 fruit here. We see 4 instances, but this one has a multiplier of 2, so that one counts for 2. So that's why it says, well, this trunk has 5 fruit, because with a cluster of 2 around the mango, it makes that mango look like 2 mangoes. And so that's the answer for F and also for G. So because of the harvesting, putting 2 mangoes in the bag when it looks at this cluster, it should actually look like this. So there are 4 mangoes and a peach. And then when you multiply that by 3, again, it should behave as if you had this tree 3 times in a branch. So it should be equivalent. And it'll, because it'll just repeat the harvesting, it'll give you, or in the size, it'll multiply the size, it'll give you size 15. So as we said earlier, yes, composite and decorator are the key patterns here. We did not use abstract factory here, although the abstract factory pattern is a useful one that could be used in conjunction with these kinds of component hierarchies. Right, except here we didn't have to. But the way that works is, for example, if you have different kinds of graphical widget hierarchies, and you want to have a program that, let's say, puts together a user interface with a certain tree structure, and you want to be able to plug and basically plug in different factories from which the widgets are actually chosen. So then you might get, without changing the code that builds the UI, just by switching from one factory to another, you could have a UI built from, let's say, one set of widgets or a UI built from the other set of widgets. Okay, like native versus platform independent. Okay, so abstract factory as a creational pattern allows you to decouple basically the responsibility of building a structure and the responsibility of deciding which element of the structure should be of which class for entire kind of groups of related classes, related building blocks. And therefore also abstract factory is in the category of creational patterns, whereas composite and decorator are in the category of structural patterns, and strategies in the structure of behavioral patterns. So you have examples of all three here among these very common patterns. Right, so here you have so you have creational. So most creational patterns are kind of wrappers around the new operator. Then you have, these are structural, which we saw. They allow us to build nice hierarchical, complex nonlinear structures. And strategy is a behavioral one. And strategy, we haven't talked about it explicitly yet, but you've seen this all over the place. Strategy is so common. Really common example is when you sort a collection, okay, you can have a sort method, and you observe that the code for sorting a collection in ascending order and the code for sorting a collection in descending order is basically the same. There's just one difference. Which method you use to determine the ordering, the comparison method. Okay, and that's why for example, very commonly, but also in the Java collections API, Java util collections. There's a sort method somewhere. Okay, there are different versions, but there's one here that says, okay, the thing we're sorting is the list, and then we're passing in a comparator, which says, how do items of this list get compared, and that is a strategy, because it means it's a pluggable piece of the behavior of the algorithm, and that also makes it a behavioral pattern. That's why it's classified in this way. All right. Now the true-false ones quickly. So the last one, I basically didn't make any deductions because I looked at it and I said, well, I should really have said, we must, we must define the corresponding method in the shape interface, and then it's false, because we just define a visitor class, but I didn't clarify shape interface versus visitor interface, so I said, okay, let's give everybody that half point. The other stuff, okay, so we saw from these earlier little examples, that so these examples suggest that yes, we can always make a tree that uses cluster nodes look like a much bigger tree? That's, after all, the purpose of cluster. And it's actually indistinguishable in terms of size and harvest. So the behavior is the same. Therefore, the answer here is true. Yes, we can always replace a tree with explicit multipliers by one with clusters, or vice versa, right? And which design principle expresses this what is called semantic subtyping? Strong kind of behavioral semantic subtyping, as opposed to simply the language allowing us to make the substitution. This goes much further, because we could write these classes in such a way that the language would allow us to make the substitution, but you get a different size if there are clusters than if there aren't clusters. Okay, so if there's explicit repetition instead of a cluster, if you got a different size, then it would be a violation of the Liskov substitution principle. So it is the Liskov substitution principle, or LSP, that describes this design issue or principle. So in general, the LSP is important to satisfy, because otherwise the language allows you to substitute, but you get different results when you make that substitution. So this could lead to unexpected behaviors, and unexpected behaviors are always a problem. When you expect something to work, but it works differently, but you don't get a crash or anything, that's always undesirable. All right, so 3L and M. As we saw, if we add by adding the cluster, we didn't need to do anything to fruit or branch, right? We could leave those alone. So 3L is true. To add something like the harvest method, we have to put that, if we add that to the tree interface, we then have to add that method everywhere we have a class that wants to implement that interface. In other words, that's also true. Meaning, when you're doing a composite hierarchy without visitor, it's easy to add new kinds of things to the hierarchy, right? But it's harder to add uniformly a new behavior to the hierarchy. That's why visitors were invented, to make it easy to add new behaviors. And you saw that in the project. You added bounding box, you didn't have to touch any of the shape classes, right? So that's kind of cool, right? But the price is, if you want to add another kind of shape, or any kind of variant to the hierarchy, then you have to change what? So in project 3, let's say in project 3, if you added square or ellipse, what classes would you have to update accordingly? The visitors. That's right, exactly. You would have to put a branch for that, a method. The methods correspond to the branches in the visitor pattern, to those branches we discussed earlier. So you would have to update all the visitors and add a branch for the new kind of thing in the hierarchy, in the structural part. So in other words, 3N, the answer is false, and for 3O it's also false. So in other words, the test summarizes this trade-off. That was the purpose of this test, the learning outcome I was hoping for. To understand the trade-off between having composite and decorator without visitors and composite and decorator with visitors. So in one, it's easy to do certain things. In the other, it's easy to do other things. And yeah, so visitor is a little complex, but it has this payoff of being able to add behaviors very easily. And it makes sense because of this issue of adding, of making it a little harder to add classes to the hierarchy. Visitor makes sense when the hierarchy is stable. So for example, when this hierarchy represents a language that is already defined and is unlikely to change, right? And then you just want to put more behaviors without having to change the hierarchy. Visitor is actually a good choice. So it's used widely in language implementations like compilers, any kind of, in tool chains for compiling and running programs, or domain-specific languages, any of those kinds of things. And one example is the Google Web Toolkit Gw, which allows you to write basically your interface to a web application, which is usually JavaScript based. It allows you to write it in Java, and then it gets compiled automatically to JavaScript. So this uses the visitor pattern quite heavily. All right, that's it. Any questions, comments? All right, so let's take a 5-minute break, then we'll move on to some other stuff.